Models for population growth. One model for the growth of a population is based on the assumption that the population grows at a rate proportional to the size of the phenomena. That is a reasonable assumption for a population of bacteria or animals under ideal conditions. Unlimited environment, adequate nutrition, absence of predators, immunity from disease. Let's identify and name the variables of this model. T equals time, the independent variable. Big P equals the number of individuals in the population, the dependent variable. The growth rate of the population is the derivative, the derivative of big P with respect to T. So our assumptions that the rate of growth of the population is proportional to the population size is written as the equation number one, the derivative of big P with respect to T equals K big P, where K is the proportionality constant. Equation 1 is our first model for population growth. It is a differential equation because it contains an unknown function big P and is the derivative of big P with respect to T. Having formulated a model, let's look at its consequences. If we rule out a population of 0, then big P of T is greater than 0 for all T. So if K is greater than 0, then equation 1 shows that big P prime of T is greater than 0 for all T. This means that the population is always increasing. In fact, as big P of T increases, equation 1 shows that the derivative of big P with respect to T becomes larger. In other words, the growth rate increases as the population increases. See figure 1, the family of solutions of derivative of big P with respect to T equals Kp. Let's try to think of a solution of equation 1. This equation asks us to find a function whose derivative is a constant multiple of itself. We know from chapter 3 that exponential functions have that property. In fact, if we let big P of T equal big C times e to the power kt, then big P prime of T equals big C of k times e to the power kt equals k open big C times e to the power kt close equals k big P of T. Thus, any exponential function of the form big P of T equals big C times e to the power kt is a solution of equation 1. In section 9.4, we will see that there is no other solution. Allowing big C to vary through all the real numbers, we get the family of solutions big P of T equals big C times e to the power kt, whose graphs are shown in figure 1. But populations have only positive values, and so we are interested only in the solutions with big C greater than 0. And we are probably concerned only with the values of t greater than the initial time t equals 0. Figure 2 shows the physically meaningful solutions of putting t equals 0. We put big P of 0 equals big C times e to the power k times 0 equals big C. So the constant big C turns out to be the initial population, big P of 0. See figure 2, the family of solutions, big P of T equals big C of e to the power kt, with big C greater than 0 and T greater than or equal to 0. Back to the text. Example equation 1 is appropriate for modeling population growth under ideal conditions, but we have to recognize that a more realistic model must reflect the fact that a given environment has limited resources. Many populations start by increasing in exponential manner, but the population levels off when it approaches its carrying capacity big M, or decreases toward big M if it ever exceeds big M. For a model to take into account both the trends, we make two assumptions. The derivative of big P with respect to t approximately equals k times big P if big P is small. Initially, the growth rate is proportional to big P. The other assumption is the derivative of big P with respect to t is less than 0 if big P is greater than m. Open big P decreases if it ever exceeds big M, close. A simple expression that incorporates both assumptions is given by the equation 2. The derivative of big P with respect to t equals k times big P open 1 minus big P over m, close. Notice that if big P is small compared with big M, then big P over big M is close to 0, and so the derivative of big P with respect to t is approximately k big P. If big P is greater than M, then 1 is big P over big M, then 1 minus big P over big M is negative, and so the derivative of big P with respect to t is less than 0. Redoing that sentence, notice that if big P is small compared with big M, then big P over big M is close to 0, and so the derivative of big P with respect to t is approximately k big P if big P is greater than M. Then 1 minus big P over big M is negative, and so the derivative of big P with respect to t is less than 0. Equation 2 is called the logistic differential equation and was proposed by the Dutch mathematical biologist Pierre-François Verhulst in the 1840s. As a model for world population growth, we will develop techniques that enable us to find explicit solutions of the logistic equation in section 9.4. But for now, we can deduce qualitative characteristics of the solutions directly from equation 2. We first observe that the constant functions big P of t equals 0 and big P of t equal m are solutions because in either case one of the factors on the right side of equation 2 is 0. This certainly makes physical sense. If the population is ever either 0 or at the carrying capacity, it stays that way. These two constant solutions are called the equilibrium solutions. If the initial population big P of 0 lies between 0 and big M, then the right side of equation 2 is positive, so the derivative of big P with respect to t is greater than 0. And the population increases. But if the population exceeds the carrying capacity, open big M greater than big, but if the population exceeds the carrying capacity, open big P greater than big M, close, then 1 minus big P over big M is negative. So the derivative of big P with respect to t is less than 0, and the population decreases. Notice that in either case, if the population approaches the carrying capacity, open big P approaches M, big M, close, then the derivative of big P with respect to t approaches 0, which means the population levels off. So we expect that the solutions of the logistic differential equation have graphs that look something like the ones in figure 3. Notice that the graphs move away from the equilibrium solution, big P equals 0, and move toward the equilibrium solution, big P equals big M. See figure 3. Solutions of the logistic equation. equilibrium solutions.